Welcome to Chapter 12 Homework Solutions Screencast. I'm very excited that I did this quite colorfully. I mean, not quite as much as Samantha and Ellie do in their notes, but, not bad for me. At any rate, I'm going to go through these. Even after going over these and trying them, you probably are still uncomfortable with this. So we are going to have some practice after break, even when we get into electricity. We're probably going to have a test at some point over this stuff in January. So while we're working in electricity, we're going to still be working on how to improve your understanding for this moment of inertia, rotational inertia, angular momentum, all this stuff, because I think it's challenging. Before we have our AP exams, I'm going to give a fair amount of practice on it as well. So that's kind of when we took that dual exam thing this year, this part of what we're doing is having to overlap a little bit. At any rate, getting started with these. For problem 13, it's asking you to find the center of mass of this situation. So essentially what I've got is I've got 4 points, and we're assuming this is at the origin. So these two 200-gram masses are at 10 centimeters to the right of the origin. These two masses are 0 in the x direction. So we take mass times the distance plus mass times the distance. We get the summation of that all over the total mass. We get 5.71 centimeters. It's only 8 centimeters up, so these two would cause center of mass to be above the x-axis and a certain amount in the y direction. 200 grams times 8 centimeters plus another 200 grams times 8 centimeters divided by the total mass again. So that's 4.57 centimeters. So if the axle passes through this, so if I was shooting this straight through here, each of these are acting as a point source at a certain distance away from this. So if this whole thing was spinning, this would be at 8 centimeters away from the axle. This would be at 10 centimeters away from the axle. This, well, I had to calculate that, and that'd be 12.8 centimeters or 0.128 meters away from the axle. So if the axis passes through A, I'm going to find the sum of the moments of inertia for points B, C, and D. And those are all mr squared since they're point sources. So I did D plus B plus C because I kind of screwed up with how I did that, but it ends up being 0.0656 kilogram meters squared. Problem 18 is asking you to find the net torque in this system. We've got something that's rotating. It's got a 0.02 meter radius because I think it was a 4 centimeter diameter, because of course they say things in diameter. And so to get the clockwise torque, this 30 newtons is pulling perpendicular to the axis of rotation at 2 centimeters away, so I get 0.6 newton meters of torque. Counterclockwise, I get 20 times 0.02, that's 0.4 newton meters of torque. The net torque is 0.2 newton meters clockwise, and since clockwise is negative torque, that's negative 0.2 newton meters. For this, I thought was kind of interesting. So it's asking you to find the angular velocity in problem 24 when we have the torque and the time. So this is analogous to force versus time, which would be an impulse graph. So this is angular impulse, and you're given the moment of inertia. So there's a couple ways you could do this. One would be if the object started from rest, you could find the net torque is equal to the moment of inertia times the angular velocity. Change in angular velocity, pardon me. So the area of this is 2 newton meter seconds. So that's the torque times the time. That's the angular impulse area of that graph. And then that equals moment of inertia times change in angular velocity. So this is equivalent to Ft equals m delta v. You might not have thought about that. An alternate method would be to use this formula. Angular acceleration is equal to torque divided by moment of inertia to get angular acceleration. So the angular acceleration here is going from 0 to 0.5 radians per second squared. So if you think about an acceleration time graph, the area of an acceleration time graph tells us our change in velocity. The area of an angular acceleration versus time graph tells us our change in angular velocity. Well, 2 times 0.5 times 1/2, because it's the area of a triangle, that would also get me 0.5 radians per second. So I'm going to have this. Don't know why I did this. Gotta try to make this a certain color. Let's make it more purpley again. Maybe make it a little bit bigger. So this is going to say area equals 0.5 times 0.5. Actually, I'll do 1/2 times 0.5 radian per second squared times 2 seconds. I have got to get my parentheses under friggin' control here. That took too long. Okay. And that equals 0. Stop it! Radians per second. Well, I am not going to do that again. Okay. So over here then for P31, we've got a pivot. It's got a 4 kilogram cat here, a fat cat here, 5 kilograms, tuna over here, and this cat's trying to walk toward it, and it's saying, how far would this cat be for this to be in equilibrium, rotational equilibrium? So I've got this distance here, don't know what it is. This 2 kilograms times 2 meters from the center plus 4 kilograms times x equals 5 kilograms times 2 meters from the center. Why 2 instead of 4? Well, because it's 2 meters away from the fulcrum, so we always measure those distances from the fulcrum. So this other cat has to be 1.5 meters to the left of the fulcrum. If it asked the distance from the left side, then I would say that it would have to be 0.5 meters from the left side. So for P32, it says a car tire is 60 centimeters in diameter, so I immediately changed that to radius. The car is traveling at 20 meters per second linear speed. So to get the angular velocity, V over R, 66.7 radians per second, but it asks for it in RPMs, which is revolutions per minute. So radians per second times 1 revolution over 2 pi radians times 60 seconds over a minute gets me 640 revolutions per minute. So that's why your tires wear out. The speed at the top point is going to be double the average. The speed at the bottom point would be 0 because at that instant it is touching the ground. For problem 45, you've got something here which is a rod. It's 2 meters in length, a mass of 0.5 kilograms. It's asking you to find the angular momentum of this. So in this particular case then, I've got, and this is, like I said, 500 grams, so that's how I got 0.5 kilograms. So it's I times omega. Well, for a rod rotated about the center, that's 1/12 ml squared, L being the total length, times the angular velocity. Well, it's giving to me wow, that's great, 120 RPMs. So again, I'm going to convert that to radians per second. So 1/12 mass length squared times 12.57 radians per second, I get 2.09 kilogram meters squared per second as my angular velocity. 62 is a fun problem, I think. So I've got this person hanging out here 4 meters from the left side. I've got a cable. The cable is only rated for 15,000 newtons, and he's eating his lunch out here, so that's great. And this rod is 1,400, or this beam is 1,450 kilograms. So this guy's living life almost on the edge. Not literally on the edge because he's 2 meters from the edge, but close. So in this case, if this is in equilibrium, I need to think about torques being equal, counterclockwise and clockwise, and the torques caused by different things equal to the perpendicular force times the distance. Since I don't know the interaction of this wall, I'm going to put the pivot here, or the fulcrum there, and I'm going to say that this cable is causing a counterclockwise torque because a component of it is acting vertically upward. This is causing a clockwise torque, and this person's mass out here is causing a clockwise torque as well. So the cable is going to be located at 6 meters times the tension times sine of 30 degrees. That equals 3 tension times meters. The clockwise torques would be mg times the distance away. Well, the center of mass of the beam is 3 meters away from the left side. The person eating his lunch is going to be 4 meters from the left side. So I get that amounts of torque. Well, this is divided, so I divide those by 3, and therefore I get the tension is going to be 15,255 newtons, and that is something they should be worried about. Yeah. So yeah, they should. Problem 69, I did 3 different ways. You may want to look at this carefully in the PDF part. So you've got a pulley here, 12 centimeters diameter, so 0.06 meters radius. There's a solid disc up here, has a mass of 2 kilograms, 4 kilograms over here, 2 kilograms over here, 1 meter to the ground for the 4 kilogram mass, and it's asking you to find the time it takes to hit the ground. So really what we need to find is the acceleration of the linear acceleration of this system. That's the big idea. Method 1, I did this like I did in class. Oh, and it says there's 0.5 Newton meters of torque caused by friction. So that's a little bit of miss. So if I think of this as a force problem, I'll have F net over M equivalent. Well, the net force on the left side would be 4 times 9.8, the net force on the right side, 2 times 9.8, and minus force of friction. So how do I find the force of friction when it says it's a torque? Well, since these two are acting on the outside, and I know that the torque caused by friction is 0.5 Newton meters, I could think of that as an equivalent force also on the outside. So that 0.5 Newton meters would be equivalent to a friction force of a certain amount at 0.06 meters from the center. So that torque, that friction really might not be acting at the outside, but it's causing a torque which could let us think about an equivalent force on the outside. And that was 8.33 newtons. So when I did that, I just subtracted that off. So I had this becomes 39.2, this becomes 2 times 9.8, this becomes 8.33. The other thing is, remember when I do my method, which is a sneaky method, I'm thinking about the equivalent mass. Well, the 4 and the 2 kilograms are still having to be accelerated, but this pulley has a mass of 2 kilograms, but on average, that pulley's mass is acting halfway out from the center. So if I have that pulley's mass acting halfway out from the center, let's see if I can do this. God, I said I wasn't going to do this again. It would be something like this. Let's have this not be a color. Let's have this be something like maybe a dashed line. Okay, yeah, so that's about where the pulley's mass would act. That worked much better than before. So if the mass is acting here, but the torques are acting on the outside, it acts as if it only has that equivalent mass of 1 kilogram. So I could divide by my equivalent mass of 7 kilograms. I get 1.61 meters per second squared. Hey, now it's easy. It's a delta y equals 1/2 at squared problem. For method 2, so this is, I'm thinking torques. So this method I had to use some torques, but I was really thinking net force over mass. So in this case, I figured out the torques counterclockwise. So that's 4 times 9.8 times 0.06 meters away. Torques clockwise, 2 times 9.8 times 0.06 meters away. And then I added the frictional force to the clockwise torque because it is opposing the acceleration. So therefore it would be acting basically in the same direction as this 2 kilogram mass as torque would act. So now I just have the net torque. Clockwise is 1.676, net torque counterclockwise 2.352, net torque overall 0.676 Newton meters counterclockwise divided by the radius. That gets me my 11.27 newtons equivalent. And I go back and do this again, same thing as part 1 up here. Method 3, I'm using net torque and moment of inertia to get angular acceleration, and then converting that to linear acceleration. So if I think of the moment of inertia of the system, the 4 kilogram mass and the 2 kilogram mass, which are hanging here, are acting like point sources on the very outside. So I'd say those are mr squareds in terms of their moment of inertia. And then the pulley itself, notice I'm not using the equivalent mass here, I'm using the total mass because I really am finding the total moment of inertia. 1/2 times 2 kilograms times 0.06 meters squared. So the total moment of inertia is 0.0252 kilogram meters squared. Angular acceleration, net torque over moment of inertia. I had figured this out already up here in method 2, so I'm not going to do it again. And I get 26.8 radians per second squared would be my angular acceleration. Well, if I know my angular acceleration, I should be able to get my linear acceleration by taking that angular acceleration and multiplying by the radius. And once again, then I get my 1.61 meters per second squared acceleration. Y equals 1/2 at squared, I get 1.11 seconds. So I did this, like I said, 3 different ways, just for you. Problem 74 was a parallel axis theorem. I did an example of that in class. So it says a 5 kilogram, 0.3 meter radius solid disk rotates on a plane held at center of mass is the same height as this axle. Well, this is annoying. So that's the axle over here. So what's the initial angular acceleration? Well, the center of mass is 0.30 meters away, so this is a gravitational torque. So 5 kilograms times 9.8 times that distance is 14.7 newtons. What's the total moment of inertia? Well, this would be mr squared if it was rotated about the center. Half mr squared because it's a solid disk. But I have an additional md squared because it's rotated about this axle on the edge. So this is what I'm looking at. Well, as it turns out that d for the md squared is actually equal to the total radius, r. So actually, the fact that it's being rotated about the edge gives it a greater moment of inertia just due to the parallel axis theorem than the moment of inertia caused by the disk itself. So these two things add up to that moment of inertia. Torque divided by moment of inertia gets me angular acceleration. Okay. The second part is now thinking about the angular velocity when it's directly below the axle. So this thing is going to pivot down. So it was initially up here and pivot down here. So this is actually an energy problem. So I think of EI equals EF. You might think that the initial gravitational potential energy would equal rotational kinetic energy plus linear kinetic energy, much like we saw in the example I did in class. But actually that's not true, and I was kind of confused by that. But since this is only rotating and none of that kinetic energy is basically going in a straight line downwards at this point, it really only has rotational kinetic energy about this axle at that point. So very odd. At any rate, when I do that, mgh equals 1/2 I omega squared. Well, I had already figured out the moment of inertia up here. I know this mgh, and I'm trying to find out the final angular velocity. So that's how I do that. Like I said, I think these are kind of complicated, and hopefully we can go over some in class, and hopefully they make sense when we go over them, as well as other examples we do. Thanks.